This lecture, I want to go through nomenclature related to benzene. And so let's just get right into the IUPAC stuff. So IUPAC naming of substituted benzenes. That is to say, if we just look at benzene by itself, the IUPAC name for this molecule is just benzene. Okay, it's not cyclohexatriene, it's just benzene. Okay, now with that in mind, that simplifies our life, because if we see something like this, we call this difluorobenzene. If we see a molecule that has, excuse me, that's fluorobenzene. If we put two fluorines atom, then it's difluorobenzene. Difluorobenzene. Now, we should qualify this by putting some numbers so that we can recognize 1,2-difluorobenzene from 1,3-difluorobenzene. Where here you pick a substituent and give it the lowest number possible, and then you pick a substituent to make number one. Usually it's the highest priority element. If there's a tie, as in the case this difluoro, then we're going to see just one of them get one, and then you give a number to the second one so they have the lowest numbers possible. Now, there's a special naming for disubstituted benzenes. And that is the Orthometapara nomenclature. This is fairly important, not just for the purposes of getting the IUPAC question right on a test, but also just in general for understanding how things are positioned around a benzene ring. If we've got some substituent, which we're going to label as a star, and we have let's have an R group. We say that the R group is ortho to the substituent with a star. So this is ortho. That's when these things are right next door to each other. And we could have the star in our group position this way. Any way that they're just right next to each other, this is ortho. Now that's in contrast to a situation where we've got the group over here, which is the same as if the group is over here. In this case, now that we're one carbon separated, one kind of free benzene carbon separated from the two substituted carbons, we say that that's meta. And then if they're across the ring, the two substituents, there's only one way to be across the ring, we say that those are para to each other. So the R group, over in the second example, the R group is meta to star. And over here, R group is para to star. Now, these are important things to keep in mind. We're going to use these quite a bit, but what this does is this changes how we approach some IUPAC naming. We would call this molecule 1,2-difluorobenzene, as I have indicated up above, or we would call it ortho-difluorobenzene. So the ortho completely replaces the 1,2 requirement, the numbered requirement. And that means that this molecule here is meta-difluorobenzene, because now we have that one carbon separating. And if we had a situation like this, where you have to think to yourself, okay, is the fluorine's more electronegative, but is it a higher priority? It turns out the chlorine, the bigger element's the higher priority. So we would call this 1-chloro 4-fluoro benzene. And maybe I should take a second to number these. So 1, 2, 3, 4. The chlorine got the lower number, the number 1, because it was the biggest atom. But you could also call this para-chlorofluorobenzene. Para-chlorofluorobenzene. Okay. We'll get to some examples where it makes a little bit more sense. When you have these different substituents, I like the 1 and the 4 better here, but we'll look at some other examples. Okay. Before we go into that, let's talk about let's do a tri-substituted example. So let's say we've got chlorine, chlorine, chlorine. Okay, so what we have to do is assign the numbers so that we have the lowest sum total possible of the numbers. We go 1, 2, 3, 4 for our numbering scheme. We can't use Orthometapara here in our IUPAC name because we now have 3 substituents. What we could do is we could say there's a chlorine that's ortho and para to the first chlorine, the 1 substituent chlorine. Okay, so this would be 1, 2, 4 trichlorobenzene. And that gives you the lowest number possible, no matter where you want to start. If you wanted to make the number 2 carbon number 1, then you have bigger numbers. So what you want to do is just kind of check to make sure the sum total of the numbers adds up to the lowest numbering possible. Then what I do is change my starting position, go clockwise, counterclockwise, try a few things. Okay. There's a new substituent that emerges that we'll see a lot of when we look at benzene, and that is the nitro group. The nitro group is when we have an NO2 hanging off of a ring. This has a tricky resonance contributor because we're locked in a charge-separated species. We've got our N plus and our O minus. Okay. And no matter how you consider this as a resonance structure, you have to have an N plus, and that's because if we try to neutralize the charge, we immediately break the octet on the nitrogen atom by exceeding 8 electrons. So we would have to push the electrons from the NO double bond up and onto the oxygen atom, forcing us to always have a nitrogen with a positive charge and an oxygen with a negative charge. That's good to remember as we talk about introducing the nitro group in future lectures, that N must always be positive. Well, anyway, if we've got a nitro group, which could be drawn as NO2 for short, or if you're feeling adventurous and will have to become adventurous, we could draw a resonance contributor of the nitro group. These are both nitrobenzene. I'm going to make some pages here, sorry, while you're writing that down. So we have nitrobenzene, and maybe you've heard the term nitro before in the context of TNT. TNT stands for trinitrotoluene. It's a very good explosive. Explosives are very interesting to study for many reasons, but they actually accomplish important things for us. They're not just bad or not just used in cartoons or whatever. Anyway, so trinitrotoluene looks like this. Turns out that this is a benzene derivative. Whoop, there. With 3 nitro groups. And I like to show that the N is directly connected to carbon. Now, it turns out that I bring this up, but it doesn't at first glance sound like it has anything to do with benzene, but we can see the benzene structure in here. It turns out that we have a common functional group that contains benzene, and that is toluene. So toluene is the IUPAC for methylbenzene. So we don't actually want to call this methylbenzene. We want to just accept that this is toluene. Methylbenzene should be named as a toluene species. So what we have are kind of historically important common names for benzene substituents. And these are things that we should know. So first of all, as we mentioned, if you've got a methylated benzene, that is toluene. That is important. I want you to know toluene and be able to recognize when something should be named as toluene. In organic 1, not as critical. I'm not going to test you on and require you to know this. I mean, I may have something and you've got like a dimethylbenzene. You could call this 1,2-dimethylbenzene. You could call it orthodimethylbenzene, or you could call it ortho because the methyl groups are next to each other. Xylene. And then conversely, if that's orthoxylene, we have M-xylene or metaxylene. And that reminds me, I should indicate that you can abbreviate the O, the M, and the P, or you can, you can abbreviate ortho as O, meta as M, or para as P. So you could call this M-xylene, and you could call this P-xylene. So that's when ortho, meta, and para become super useful, is when you've got, when you're kind of using these common names, because it allows you to avoid having to number the main substituent on that common group. Okay, so I want you to know toluene. Xylene is, you know, for your own information. I won't ask you about it yet. And we have benzoic acid. Benzaldehyde. So benzoic acid is a carboxylic acid. Benzaldehyde is an aldehyde. Smells like cherries, interestingly. And then hydroxybenzene is phenol. And I want a really hard E in this name. I want to emphasize that that's phenol, not phenyl or phenol. Phenol is really helpful because benzene as a substituent is phenyl. So phenyl versus phenol, that's a pretty subtle distinction. So I would recommend phenol. Give it a nice hard E on phenol, and that's separate from phenyl. So what's phenyl? Phenyl is when you've got benzene hanging off of a molecule. And so let's imagine you've got a really complicated molecule with like a benzene hanging off of it. You would call it a phenyl something. Turns out that benzyl might make more sense, but benzyl is something else. It's a benzene with a CH2 off to the next part of the ring. Sometimes I'd want to call that a toluene, but then toluene is something else. Anyway, okay, so that's phenyl. Phenyl, or pH, is benzene ring hanging off of something. So we could say there's a phenyl group hanging off of our molecule if we're referring to just a lone benzene ring, and it should be unsubstituted. Okay, so let's go back to TNT, which is trinitrotoluene. Could add some numbers here, 2, 4, 6 trinitrotoluene. Because we're naming this as toluene, which is methylbenzene, we lock carbon 1 as the methylated position, even though that methyl group has a lower priority than the rest of the things. So 2,4,6 trinitrotoluene is us taking toluene. We have a methyl group at the 1 position, and that determines our numbering, and we have nitro groups spread out around the ring, 3 of them, hence trinitro. And then to spread them out evenly, we have one at the 2 position, 1 away from 1, 3, 4, 5, 6. Looks weird to be right next door and be number 6, but that's the Ouroboros speaking to us, which is the snake biting its tail, right? We're swinging around the ring. If there's a 1, then to the left of it and right of it in one combination. It could be either combination. We have a 1 and we have a 2 and a 6 carbon, okay? One's away from our 1 position. Okay, so that's numbering with these common names. We could look at some more examples. Let's imagine we've got the carboxylic acid. And we've got chlorines. These chlorine atoms are meta to each other, but we wouldn't include meta in this name. Instead, we would say this is 3,5-dichloro, all one word, well, not all one word, excuse me. 3,4-dichlorobenzoic, and then acid is a separate word. All right, space here, just so you know, that's a separate word. 3,5-dichlorobenzoic acid. I recognize the benzoic acid was our benzene with the carboxylic acid. I counted 1, 2, 3, 4, 5. So starting at the carbon, which is lower priority than the chlorine atoms, but we start at carbon here because it's part of the carboxylic acid that defines the common name benzoic acid. Now, I only need you to know toluene, benzoic acid, toluene, benzoic acid, benzaldehyde, phenol, and a phenyl group. Okay. So let's. I mean, we could extend the common names slightly if we have something that warrants it. Like, for example, this extra oxygen makes this a per-benzoic acid. And so we would maybe carry that common name forward. So let's put a chloro at this position. If you notice, we've only got the 2 substituents, the one that defines our common name, which is per-benzoic acid in this case. And then we've got a chlorine atom that's in the 3 position. So we could call this 3-chloro-per-benzoic acid. Or we could use 3-chloro, goodness, per-benzoic acid. I just gave a big speech about that. Per-benzoic acid. Or conversely, we could use our Orthometapara designation. So I would call this meta space chloro per benzoic acid. So this is kind of a special example. Like, you wouldn't see too many per benzoic acids. But if we've got an M, C, P, B, and an A, let's just call this M, little m, C, not P, C, P, B, A. This is our epoxidizing agent from a few exams ago. And so anyway, I just wanted to bring that up. You can use the Orthometapara if you've got one substituent off of a one of these common names. So for example, if you've got this molecule, you could call this p-nitrophenol or paranitrophenol. Okay. All right, so that's Orthometapara. That's using Orthometapara in the context of common named species, and then recognizing if we have 3 things, we can't just name them as Orthometapara anymore because there's 3, there's not 2. Okay, so that should cover the bulk of naming. Orthometapara, this is stuff that you can carry with you for the rest of your chemical career, whether that's in organic, that includes organic chemistry and beyond. And then some of these common names continue to emerge, like toluene, phenol, benzoic acid, benzaldehyde. These are things that also kind of continue onward well beyond just a test that requires you to provide some IUPAC names for organic molecules. Okay, so that'll do it for this one. So we'll end here and I'll see you next time.